Okay, hello everyone. Rick Jardine is going to speak today from University of Western Ontario. So it's a great pleasure to have him. So he was my postdoctoral supervisor between 2014 and 2017. So it's also I'm extra happy to see him here. So what he's going to tell us about is a certain algorithm for dimension reduction based on manifold learning techniques. That algorithm is called the UMAP algorithm, if I'm pronouncing correctly. So Rick, you can start.
Okay, thanks very much. It's a pleasure to be invited to speak here. I very much appreciate the invitation. As Shannons says, this is about a manifold learning technique. UMAP is the public name for it. It's an acronym, first of all, but it's the public name for a clustering algorithm for data that people imagine is near manifold. It's an incredibly successful algorithm. It was introduced by Healy-McInnes at the Tutte Institute in Ottawa in 2018. And there's a preprint from that time. And there's a paper that was published in 2020 that's much longer. I think that the preprint is still more readable. The UMAP algorithms, incidentally, if you can't hear me, let me know, okay? UMAP itself is an algorithm for it's called Uniform Manifold Approximation and Projection. It's a dimension reduction algorithm. I'll explain what that means later. The algorithm itself has a lot of moving parts. The basic idea is that data in some high dimensional space might be near some manifold, but it might be not be uniformly distributed across that manifold. And the idea is first to change the metric on the manifold to make the data uniformly distributed, and then apply known dimension reduction techniques up to a point. Okay, if you're going to change a metric locally, it's going to take you outside the safe harbor of ordinary metric spaces. So we have to use, well, what the authors use is Spivak's extended pseudometric spaces. I'll describe those. That's probably the most important part of this talk. Once you have extended pseudometric spaces, or EP metric spaces, as I say, you can run standard topological data analysis constructions on those. But you're interested in clustering. So what you end up producing from a data set is a weighted graph, and I'll describe those and how you get there. And then finally, you do a dimension reduction step that takes you out of the very high dimensional space of which these weighted graphs are located into a lower dimensional space where you might hope to see clusters. And the method that the authors use is so-called method of Laplacian Eigenmaps. But once you're there in the low dimensional space, you want to the Laplacian Eigenmaps construction only produces an approximation of a low dimensional representation of the graph, and you want to optimize it a bit. And that takes us into the sort of rabbit hole of fuzzy sets and cross-entropy, which I will describe. So there's a lot of moving parts here, and bear with me. Okay. First of all, extended pseudometric spaces were introduced by Spivak in about 2009 in a preprint that was never published. An extended pseudometric space is a set X with something that looks like a metric D on it. This D takes values in the interval between 0 and infinity, so there can be infinite values. And it has a lot of the characteristics of a metric, namely the distance from X to itself is 0. It's symmetric. The distance from X to Y is the distance from Y to X, and you also have the triangle inequality. But you can have distinct points X and Y that have distance 0 from each other. This is the sort of pseudo part. And you can have elements X, Y, or UV rather, which are infinite distance. And this is the extended part. So extended pseudometric space means just these three axioms are involved. Every metric space is an extended pseudometric space. You just include, the metric space consists of a set Y with, a distance function on it, which takes values in finite numbers, and you can include finite numbers into the full set of numbers between 0 and infinity, and you get an extended pseudometric space. Okay. A morphism of such things, of extended pseudometric spaces, is a function which compresses distance. In other words, f is a function from x to y such that the distance in y from f of x to f of y is less than or equal to distance in x from x to y. One says that the function compresses distance, and I think Spivak says that it's non-expanding. You can certainly compose two such functions, and you get a category of extended pseudometric spaces and their morphisms. Now, the big advantage of going to extended pseudometric spaces is you can glue things together. And that's done with a quotient trick. So if I have an extended, or if I have a set X with an extended pseudometric on it, and if I have a function, a surjective function from X to another function Y, for elements X and Y in Y, I can set the distance from X to Y to be the infimum of distances along a polygonal path which maps down to X and Y in some sense. In other words, you look at all pairs Xi, Yi, as I, for some finite set list of such things, such that P of X naught is X, P of X1, P of Y naught rather is P of X1, and so on. And the last pair, P of YK is Y. These distances are computed in X, and you look at the smallest, or you look for the smallest number as you iterate through all these so-called paths. And that gives you an extended pseudometric on Y when you define the distance function that way. It's not hard to see that at all. And there's a quotient map from the original extended pseudometric space to this new extended pseudometric space Y, which satisfies the obvious universal property. So what that means is that the category of extended pseudometric spaces has all small colimits and categorical sets. It's co-complete. So if you want to construct an underlying, in general, the underlying set of a colimit is the colimit in sets in the extended pseudometric space category. If you want to construct a disjoint union of extended pseudometric spaces, you just take the disjoint union of the underlying sets and you set the distance between X and Y to be the distance on the ith term if both elements lie in the ith term, and it's infinite otherwise, okay? So distance between the various summands in a disjoint union is infinite. Okay, and co-equalizers and or pushouts are given by this quotient construction that I just described. So you have a co-completeness here, which is important, and you couldn't do that with metric spaces. Okay, so once you have this category of extended pseudometric spaces, you could talk about finite extended pseudometric spaces, just like a data set is a finite metric space. And you could roll the topological data analysis tape for such things. So if I have an extended pseudometric space or EP metric space with distance d, and if I take a particular number s, a parameter s between 0 and infinity, and I'm going to describe this in a funny way in terms of posets. So the poset that I'm calling P sub s of x is the poset of all subsets of x, such that the distance between any two elements is less than or equal to s for all x, y in this subset, okay? There's a corresponding thing underlying the Vietoris-Rips complex that you might know from topological data analysis. A poset like that is closed under subobjects, so it describes an abstract simplicial complex, and that's what people would commonly call a Vietoris-Rips complex, but I prefer to take this poset and take its nerve. That nerve is the barycentric subdivision of the Vietoris-Rips complex, and it shares that homotopy type. So it's well known in simplicial homotopy theory that if you take an abstract simplicial complex like the S of x, take the corresponding nerve of simplices, and take the take the corresponding poset of simplices and take the nerve of that, then there's a last vertex map from the nerve of the poset of simplices to the original simplicial complex, which is a weak equivalence. Now that is subject to imposing a total ordering on X. When people talk about simplicial complexes as simplicial sets, there has to be a total ordering around. But this functor, which takes a set X to the nerve of this poset, does not use a total ordering on X. And in fact, that weak equivalence is the way that you show that the constructions that you do on the simplicial complex level are independent of the ordering of the vertices. So when I say Viator-Strips complex, I'm going to mean nerve of this poset. There's lots of reasons for taking that to be the basic definition. In particular, you can manipulate homotopy types a whole lot easier because you can just do them in category theory. Okay, so that's going to be my starting point. I'm going to take the nerve of these posets that I'm talking about. I'm going to write V sub S of X and just identify this nerve with the Viator-Strips complex. And when I want to specify the underlying metric, I put the metric in the notation. So S varies, of course. So you get a diagram of simplicial complexes or simplicial sets by letting S vary. And that's sort of the underlying construction in topological data analysis. So you can just essentially roll the same tape. So you could look at these Viator-Strips complexes or these nerves and take their homology with coefficients in some field that say K and let S vary. And when you do that, you define persistent homology for the extended pseudometric space, this finite extended pseudometric space. And it just generalizes what you might call persistent homology for an ordinary finite metric space. Now, this is a diagram of spaces as S varies. Those spaces have path components, and the path components of those spaces are clusters. These are iterated partitions of the underlying set, the underlying data set. And that's what everybody calls a cluster these days. It's a partition of the data set. But S is varying, so you can talk about persistent clusters and things like that. And the way people usually organize that is within a hierarchy. You can start with your data set X, and with this extended pseudometric on it, then you construct a tree with vertices where the objects of the vertices, for the vertices themselves, consist of pairs consisting of the parameter and a path component in the corresponding Viator-Strips complex for that path component. And you say that this pair is less or equal to that pair. This is really a poset. If S is less than or equal to T, and you're talking about the same path component here, okay? All right, so that tree construction is traditionally the source of hierarchical clustering algorithms for finite metric spaces. And you can imagine it's the same thing for extended pseudometric or finite extended pseudometric spaces. Now, in practice, one cares most about the co-limit of these Viator-Strips complex for S less than infinity, okay? And that is a disjoint union of simplicial sets, which I call global components. And each of those global components consists of simplices having edges of finite lengths. So two elements are in the same path component. If you can get to one to the other through one simplices of finite length, okay? And you can't always get from one point to the other, so there's path components involved, which are the global components. Now, each global component is contractible. It's filtered by the distance, maybe, or the weight. I'm starting to introduce the word weight here. And so if you restrict yourself to just thinking about a global component and letting S vary, it's more like the traditional topological data analysis construction, where you're filtering a contractible space. Okay. Now I have to describe what I call the UMAP complex itself. You start with a finite data set or a finite extended pseudometric space, but of course, this is supposed to be about the study of very large data sets. So the data set in this case is very big. Okay, so you look at each element in the data set and choose a neighborhood set for that data set, which is points distinct from it. And it's a finite collection of points, and then you just essentially add them up. So I take X, I take X and its set of neighbors, and I call that the union U sub X. And I do this for each element X in the data set. And of course, it sits inside the big data set X. Now, the standard example is to take N sub X to be the so-called K nearest neighbors in the data science set. I mean, the K elements which are closest to X itself. But these might be hard to find in very large data sets, but there's algorithms that approximate them. And so you run an algorithm to find the K nearest neighbors for each element X of X. All right. Now, here's the construction. You have this set consisting of X and its K and its neighbors. And you want to construct some sort of a metric on that, a notion of distance. So each one of these neighbors, if you look from X to Y, it's got a distance from X to Y. So that two element set is an extended pseudometric space. And so you have these two element extended pseudometric spaces. They're all glued together at the point X. And so it's a set of rays. And you can form the wedge sum over the element X inside extended pseudometric spaces. And that gives you an extended pseudometric on this set U sub X that I'm talking about here. So you do that for each element X. And it's relatively easy to see what a distance between 2 points should be inside the set. You just go down to X and back up as much as you need to get the distance from Y1 to Y2, where Y1 and Y2 are members of the neighbor set. Okay, so for each X, you've got an extended pseudometric that defines the distances. Now, these distances, they can be the underlying distance, or they can be some sort of weight that you assign. Just a positive number is all you care about. And that's the way the construction goes in the Healy-McInnes paper. So either choose distances or weights. You take these local extended pseudometric spaces for each element X and X. You can take this local guy and extend it to something global on all of X by just treating X itself as this U sub X disjoint union of a bunch of points. So that's telling you that the distance defined by X from Y to Z should be infinite if either Y or Z is outside this set U sub X. Okay, so that gives you a collection of extended pseudometrics on all of X, which varies with the element in the data set. Okay. Now, X sits inside all these extended pseudometric spaces, just as a set of elements. And so X sits inside the corresponding Vittori-Ripps complexes just as a set of discrete elements. It's a set of discrete elements in the diagram theoretic sense, except because these Vittori-Ripps complexes are diagrams of simplicial sets which vary with the parameter S. But X sits inside them. So you have a perfectly good inclusion of a discrete thing into this simplicial thing for each element in X. And so this is a comparison of diagrams, and you can form their wedge summand where you glue together over the elements of the original data set. And this iterative pushout, if you like, is what you would call the sort of UMAP complex for the set X. That's what it is. It's a diagram of simplicial sets defined on an interval of numbers between 0 and infinity. Okay. So forming an iterated push-out of diagrams might seem a little strange, but to somebody that's experienced with simplicial sets, it's just a triviality. You just do it. All right.
Rick, I have a question. So when you choose these dy, so the distances on ux dx, right? So the d sub y's, so you said they're rather arbitrary, right? They don't really come from an
yeah, well, this is wrapped up in how Healy-McInnes choose a weight because they adjust the distances. Okay, and they adjust distances so the farthest element in a nearest neighbor set has distance 1. Okay, from the original set x. Okay, so you divide by this distance to the farthest neighbor. You take the original distance and divide by the distance to the farthest element in the nearest neighbor set, and you get a new number. But that new number is positive. It can function as one of these elements d sub y, or as one of these numbers d sub y. So this is what I meant by arbitrary. I mean, you're entitled to use whatever positive numbers you like there, but Healy-McInnes use a particular construction. Does that answer the question?
Yeah, so the other question is the n in the notation vxn. This is just a notation, right? The n.
The n stands for this choice of neighbors.
Neighbors.
Okay. Okay.
Okay. Yeah. Thanks.
Sorry. Okay. So we've got our UMAP complex, which is really a diagram of simplicial sets, but it's constructed locally in a funny way as a wedge. All right. Now, I'm not sure that fuzzy graph is the right word for the next construction or not, but if you can construct a graph out of this complex that I described, and it's a weighted graph, and it's a diagram taking values in graphs that varies with this parameter s. S slides between 0 and infinity. And this graph for a particular parameter value s has the elements of x as vertices again, but the edges are 2 element subsets of x whose distance is less than s inside an extended pseudometric space. Okay, that's fine. And of course, as s varies, one graph maps to another, so you have a diagram of graphs. Okay, I call this construction, this functor taking values in graphs, the fuzzy graph for the finite extended pseudometric space x and d, and it's a functor defined on the parameters from 0 to infinity. It's called fuzzy graph to keep it distinct from something else, which is about to come up. Now, if you look at a parameter value s, then this graph here is the non-degenerate part of the one skeleton of the nerve sum check construction. The check construction is what I call a check groupoid. The objects are the elements of x again, and there's a morphism from x to y if and only if the distance from x to y is less than infinity. So this is the limiting thing. It is in fact a groupoid, and it's a disjoint union of contractible groupoids because we have these these global path components. Now this nerve has this groupoid has a nerve, and you can filter the nerve of the groupoid by letting the part of it corresponding to parameter value s to consist of strings or arrows such that the length between one thing and another is less than or equal to s. Okay, so that filters the nerve of the so-called check groupoid. And now there's a functor from that check groupoid to, well, the nerve of the colimit of these posets, letting s vary, and it restricts to a map of simplicial sets from the piece of the nerve, or the piece of the check groupoid, if you like, taking values in the fundamental groupoid of the Viator-Schrips complex corresponding to the parameter value s. Pi here stands for fundamental groupoid. And this functor, or whatever it is, takes a morphism from x to y inside here to the composite consisting of these two maps in the fundamental groupoid. Okay, so it's this map, which is a perfectly good inclusion of finite sets, then you go by the inverse of that particular inclusion. Okay, and the point is finally that this graph here is the non-degenerate part of the one skeleton. So its path components, for a particular value of S, are the path components of the corresponding filtration step of the nerve of the check groupoid, which in turn looks like the path components of the fundamental groupoid. And you can just check that. It's not so hard, but the path components of the nerve are the same thing as the path components of the fundamental groupoid are the same thing as the path components of the corresponding nerve, but that nerve is the Viettor's-Rips complex. So what that's saying is that if you let S vary on the right-hand side where you're computing path components of the Viettor's-Rips complexes, you're computing clusters in a traditional kind of sense, but you can find those same clusters over in this so-called fuzzy graph for this extended pseudometric space. And this is a general construction that works for arbitrary extended pseudometric spaces. So in other words, this thing that I'm calling the fuzzy graph, this diagram taking values in graphs, when you take path components, you're essentially computing clusters for the Viettor's-Rips complex for the Viettor's-Rips, for the finite extended pseudometric space. Okay, so that's a separate thing, it's very general. All right, if you look at Spivak's preprint, he talks about fuzzy objects and simplicial sets in a traditional sense. And he has a realization construction from those things to extended pseudometric spaces, okay? And there's a singular construction going backwards, but it's all in sort of traditional fuzzy sets. But you can extract that into the current setting. And I'll explain what I mean by that in a minute. So if you're given, an extended, finite extended pseudometric space, you go through this construction with nearest neighbor complexes to construct this new extended pseudometric space for each. I mean, this is this metric local. This is local metric for each element in the point in the set X. Then I can take all of these extended pseudometric spaces now and take their wedge summand over the elements of the X, okay? And I form a new extended pseudometric space using this co-completeness construction, or this co-completeness fact in extended pseudometric spaces. And this co-element is what you would call it coincides with Spivak's realization of the UMAP complex, okay, and sometimes, okay. I don't want to say more about it than that. But on the other hand, there's an excision result. So I can take this diagram of simplicial sets that I've constructed here, where S varies through the parameter space. That is a wedge summand of corresponding things for each of these little metrics to define locally. And each one of these metrics, or each one of these extended pseudometrics, maps into this colimit thing, the X of D. So for each X, there's a map for each element X, each data point X, there's a map from the simplicial set corresponding to this local choice of metric into the global choice of metric, the corresponding thing for the global choice of extended pseudometric that you get from this co-limiting construction. And that sets up a map from the UMAP complex to the Viettor's-Rips complex for the data set X corresponding to this co-limit extended pseudometric. And what happens is if you let S vary, you'll see that this map here induces isomorphisms of path components from the UMAP complex to the Vitor-Schrips complex corresponding to this co-limit extended pseudometric. And that's for S greater than or equal to 0 but less than infinity. Okay. So I'm calling that excision because you're recovering the path components, or rather you're recovering the path components here from this co-limiting construction. Okay, and showing that, proving that, amounts to showing that, or observing that paths in both cases are hops through nearest neighbors in some sense. So you can translate between the two. So a corollary for all of that is that if you hold a parameter S fixed and look at path components of the UMAP complex corresponding to that parameter, you just saw that that's isomorphic to path components for the Vitor-Schrips complex corresponding to the co-limit extended pseudometric, but then that can be recovered from this fuzzy graph corresponding to the co-limit extended pseudometric. Okay, so all of these guys, these things that you care about in some sense, these clusters can be recovered from path components of this diagram of graphs. Now, this is not in the Healy-McInnes paper. They go by a roundabout construction. They don't use Vitor-Schrips constructions. They use Spivak singular construction. But you have to know that Vitor-Schrips construction is homotopy equivalent to Spivak singular construction. And I proved that a while back. And so you don't have to go anywhere near Spivak singular construction. And in fact, you don't need all of the UMAP complex if you're just going to talk about clusters. All you need is this fuzzy graph that's constructed directly from the co-limit extended pseudometric space, which is a much easier thing to describe. Okay, so where are we? You want to compute clusters for this extended pseudometric space. And you take the fuzzy graph, let S vary, and compute path components of those graphs. That's what you do. All right. Now, a weighted graph is just a functor taking values in graphs. Okay, that's a cheap way to describe it. And so we have this functor taking values in graphs. It's a weighted graph in the sense that I just described. I call it the UMAP graph. It's the fuzzy graph associated to the co-limit extended pseudometric space construction. And that's all you need for computing clusters. Okay, now this graph, this weighted graph, I mean, in some sense, all of data science in recent years has been about constructing weighted graphs from data sets in a clever way so that you recover clusters in some sense. Okay, so this is one of those constructions. And you're always in the context of a very big data set. So we haven't left that data set yet. It's very big. So the graph is very big. And any description of it, in terms of Laplacians or whatever, lives in a high dimensional space. And high dimensional spaces in data science are subject to what they call recursive dimensionality. And the best way I've seen to describe it is that if you have a hypercube in a high dimensional real space, and if you take a inscribed ball, there's a typo there, inscribed ball in that hypercube, then the volume of the hypercube is very much bigger than the volume of the inscribed ball. Okay, so if you have a data set sitting inside our uppercase N, then the intersection of that data set with the hypercube, this fixed hypercube, is likely much larger than the intersection or the cardinality or the number of points of X which intersect the ball. Okay, so in a high dimensional space, I mean, what the statisticians or data analysts will tell you is that data sets tend to cluster near the corners of a cube. Okay, and this is exactly what they mean by that, at least my understanding of it. And the idea with dimension reduction is to somehow avoid that somehow. And there's a variety of techniques for that. The one that Healy-McInnes, the dimension reduction technique that Healy-McInnes used is called Laplacian Eigenmaps. And it can be described very generally. It's just it's essentially just a linear algebra trick. So if you have a weighted graph, where you have graphs with edges, but each of these edges has a weight. And if it's connected, then what the idea is to find a function from the set of vertices of the graph to a small dimensional real space such that the distance between images of ends of edges is close to the corresponding weights for all edges. Okay. And Laplacian Eigenmaps is an algorithm which was introduced, I believe, by Belkin and Niyogi. I included the reference in this in the slides here. And what you do is you take your weighted graph, you take the weights, and of course, you make a matrix out of the weights. That's a symmetric matrix, and it's got zeros on the diagonal. Then you construct it, and if X is connected, then if you look along a row or a column, then you're going to encounter a non-zero element here, okay? So the corresponding diagonal matrix of sums along, that's wrong, that should be I less than J there. The sums along either a row or a column is going to be non-zero, and it's the same if you sum either along a row or a column. So what you got here is a symmetric weight matrix. You have a symmetric diagonal matrix, which is non-trivial, in each diagonal element. And the so-called Laplacian is the difference between this diagonal matrix and the weight matrix. That's a standard construction. That's the Laplacian matrix for the weighted graph, if you look in the literature. But then what Belkin and Niyogi do, and what Healy-McInnes do is to normalize it. So they construct a normalized Laplacian by pre-multiplying by the diagonal matrix consisting of square roots, or 1 over the square root of all the elements of the diagonal here. You multiply L up front by that, and you multiply on the right by the same thing, okay? That is clearly symmetric. Okay, so you can construct an orthonormal basis of eigenvectors for it. And just by tricks of linear algebra, that's positive definite. So if you choose eigenvectors for this matrix, say with eigenvalues lambda I, so Wi is an eigenvector with eigenvalue lambda I, you let y sub I be the multiple of the eigenvector by this inverse matrix. And that gives you a bunch of, say, column vectors, and you put them together in a matrix, D columns for a matrix, and you let y parenthesis I be the ith row of D. And this is a D-dimensional column vector, row vector at this point. Then again, just by tricks of linear algebra, there's a relationship like this, okay? Relating the original weights, the distances between the various rows squared, sum up I less than J, and what you get is a sum of eigenvalues, okay? And what you're doing here is you're taking a trace of, say, what is it? Y transpose L prime Y. That's what you're doing. And looking at that in 2 ways gives you this relationship. So given on this, this is just linear algebra at this point, and given this trick, what you do is you take P of xi to be the ith row of the y vector of the y column that you made out of eigenvectors. It's in d-dimensional space, and the distance between, or the square of the distance between P of xi and P of xj times y, times the original weight. Well, that's in the sum end here of positive numbers, so it's certainly less than or equal to lambda d, this sum of eigenvalues. And this gives you a relationship between p of xi and xj with the original weight. Okay, so this is just what the linear algebra is telling you. And it's easy to describe, but nobody describes it. Okay. So that's what you do. That's what dimension reduction for Laplacian eigenmaps does in general. I don't know what happened there. So if you go through all this construction, remember I constructed a co-limiting extended pseudometric space and a co-limit extended pseudometric. And I told you that the path components are important. I mean, the global components are important. And so if you look at global components and restrict your co-limit extended pseudometric to them, you'll find that that's an ordinary metric. Okay, so you've left the safe harbor of metric spaces, but you've gone back to it at this point. And it's not hard to see that just by the way it was constructed. Now, this is about, this dimension reduction trick is about extend the arbitrary weighted graphs, okay? And we've got our graph, our UMAP graph or our fuzzy graph associated with EP metric. And one of the secrets here is that the choice of appropriate weights for that graph can be a bit non-trivial. There's various choices that are available to you. You could take the weight to be just the distance between xi and xj inside this extended pseudometric space. You say that the weight is that distance if there's an edge from xi to xj and it's zero otherwise. That's like traditional Laplacian construction. Or you could say that the weight is the inverse of that distance if there's an edge from x to xi, xj, and zero otherwise. And I like this a little better because in that case, the distance between p of xi and p of xj, the square of that, is less than or equal to that weight times this number, which is the sum of eigenvalues, whatever that number is. But you see, that's saying that the distance, the square of the distance between pxi and xj is bounded above by some constant times the weight, okay? If you just invert the weights everywhere. And on the other hand, if you go to what Healy-McInnes actually say, they define the weight of the edge corresponding to xi and xj to be the exponential of minus the distance between xi and xj inside this co-limit extended pseudometric. If you read their paper, it just would look like a much more complicated expression, but this is exactly what they did at the end of the day, okay? So this assignment of weights follows the original Belkin-Nayogi description of Laplace Eigenmaps construction. And there they define the weights by analogy with a heat kernel for a Laplace Beltrami operator on some sort of manifold. And the assumption there is that all data points X are near manifold, but nothing I've done so far is dependent on manifolds. The only thing that seems to depend on the manifold is this exponential construction because it approximates something that would happen on a manifold if it were there. That's where the manifold part, the title comes in. Okay, so there's various choices of weights that you can construct. Okay, so what do we have so far? We start with a data set in a metric space, finite data set in a metric space, high dimensional metric space. You choose nearest neighbors and use these to construct an extended pseudometric space structure on the set of elements in this data set with this new metric, okay, which we constructed by wedging together metrics, which are defined locally. Okay, so this is a graph and you use dimension reduction algorithm, some sort, in other words, assign some sort of weight to and use the Laplacian Eigenmaps construction to find a low dimensional graph y with vertices yi equals pxi with actual distances, which you hope to approximate the original distance that you put in some sense. Okay. And this is by using suitable weights w sub ij, and I told you that there's various choices. There's a choice I prefer. So you have this graph sitting inside a lower dimensional space, and now you want to improve on that choice of graph somehow to better approximate the weights. And Healy-McInnes do this with fuzzy set or a combination of fuzzy set methods in the so-called method of stochastic gradient descent from statistics. Okay, now I'm not going to go too far down the rabbit hole, which fuzzy set methods present. I'm just saying maybe you can avoid it somehow. But in order to say how you avoid it, I have to say what you're avoiding. So classically, a fuzzy set is just a function from the set to the interval of numbers between 0 and 1. Okay, that's all it is. Now, Michael Barr has a paper from 1986 where he extended this definition of fuzzy sets to a fuzzy set with coefficients in a locale. So that's just a function from x taking values in this locale L. And what a locale is a poset or even a lattice. It's a complete lattice that has a distributive log. Okay, and being a lattice, that's a poset, and it also has a topology on it, and that topology can be used to construct a diagram of, well, I mean, I'm getting ahead of myself, but you can use that to describe a diagram of simplicial sets on the locale, which is essentially Viator-Schripp's construction. Okay, so lots of locales in nature from this point of view. If you take a locale L and take its opposite, that's a locale again. Okay, it has the same properties. So the interval of numbers between 0 and 1 is certainly a locale, but so is its opposite. And thought of as a poset. And the interval of numbers between 0 and infinity, where you include the endpoint, is also a locale, as is its opposites. And these are the ones you care about, at least I care about in the present context. And if you look at the classical, well, if you look at Barr's definition, which is an extension of the classical definition, a morphism of fuzzy sets is a function from x to y, such that if you look at the picture, you take psi composed with f and compare it to phi, then phi of x is less than or equal to psi composed with f at x, okay, for all x and x. In other words, in some souped up sense, if the typo wasn't present, the diagram homotopy commutes, okay? Or it compresses things. So Michael Barr would tell you that a fuzzy set is a sheaf on this locale. Well, not on this locale itself, but you have to join an extra initial object. And a fuzzy set is a sheaf of monomorphisms on that enhanced locale. And in particular, if you have a finite extended pseudometric space, then interval of numbers between 0 and infinity is the locale, as is its opposite. Then you extend a new initial object, and the Viator-Schripp's construction gives you a simplicial sheaf on that locale. Okay. Or another way of saying it, it's a simplicial fuzzy set with coefficients in the locale L. So you can do this for arbitrary locales, and that's the point. So I can do it easily for these intervals here. Okay, in classical fuzzy set theory, there's a notion of a complement. Well, you take an element, a number s between 0 and 1, take 1 minus s, that's also a number between 0 and 1. And that defines a poset isomorphism between the interval of numbers between 0 and 1 and the opposite of the interval of numbers between 0 and 1. called a dual. So if P is a fuzzy subset of X, well, this is what, I mean, just the function here is sometimes called a fuzzy subset of a set X in the classical descriptions. Its complement P upper C is defined by taking P upper C of X to be 1 minus P of X. I also call this E P of X. So, for example, every subset of a set has a step function, right? It's a function which is 1 inside X and 0 outside. And the complement, or E of that step function, is a step function corresponding to the complement of A inside X. And that's why it's called a complement construction or a dual construction. Okay, that's classical theory. And you'd think that that only works for, when your locale is the interval of numbers between 0 and 1, but you can go more generally. So if you look at the interval numbers between 0 and 1, there's isomorphisms of posets's of this form, where there's function from 0 to 1, which reverses order, which takes s to minus logarithm of s. That produces you a number between 0 and infinity. And there's an order reversing function backwards, and these are inverse to each other, and they're poset isomorphisms. Okay, phi is a really old thing. Okay, it's called Shannon's information function. It was introduced by Shannon in his sort of seminal paper in data analysis that appeared in 1948. And it's still an interesting read if you care to read it. So we've got this sort of information function bijection or poset isomorphism between these two posets. And I can use that to describe a complement for, the complement construction for interval numbers between 0 and infinity. In other words, you just compose, or you essentially conjugate by psi. So you go from 0 infinity to psi, take complement, then go backwards. Okay, and this defines a duality isomorphism from an idempotent from interval numbers between 0 and infinity to the opposite locale. And this number I call x star is the image of x under this function e, and you can just write out what it is. It's minus logarithm 1 minus e to the minus x. Okay, and you can play with that to your heart's content. And that's for all x sitting inside 0 infinity. So, of course, that's a continuous function, and x and its dual are close if x is near log 2. You can see that for yourself. All right. And I went through that because it's wrapped up in this notion of cross entropy, which is used by Healy-McInnes to approximate or to improve on choice of low-dimensional graph. So there's this notion in classical fuzzy sets of cross entropy, and the only sensible reference I can find to that is a paper of Bhandari in 1993. It's listed here. So if you start with fuzzy sets, U and V, two sets rather, then the cross entropy from B to U is defined by this horrific looking sum. Okay, and this is for finite sets. Okay. It's non-symmetric, but more importantly, if you look at it, it's a sum of summands that look like this. You have S log S over T, then 1 minus S log 1 minus S over 1 minus T. Okay? So what this is a sum of things that people have traditionally been calling Kullback-Leibler divergences since the early 50s. And this is for the probability distributions defined by the numbers S and T respectively. The probability distribution associated to S is S and 1 minus S. Okay, so throughout this discussion, U and hence this number S is fixed and V varies. And this so-called cross entropy gives you a non-symmetric measure of the distance from a fuzzy set V to a fuzzy set U. All right. So let's suppose, we're talking about numbers here which come from interval of numbers between 0 and 1. So let's suppose that these numbers came from real life. Via this information function. Okay, let's suppose that s is e to the minus y and t is e to the minus x for some numbers y and x. And f of s of t, well, that's f of e to the minus y, e to the minus t. This is this Kullback-Leibler divergence. You just substitute in, and this is what you get. You get e to the minus y times x, quantity x minus y, times e to the minus y squared times quantity x squared, e to the minus y dual times quantity x dual minus y dual. The y does not vary, x does, okay? So this number, well, its absolute value depends on distance between x and y and the distance between their duals, okay? So if I give you a pair of fuzzy sets in the sense that I prefer, and you take values in the locale of numbers between 0 and infinity, then the analog of this cross-entropy function is the cross-entropy associated to the thing you get by going back to numbers 0 to 1, and it has this form, okay? It's the sum of things over this finite set x, e to the minus x times v of x minus u of x, plus e to the minus ux dual times v of x dual minus ux dual as x varies. And for u and v, taking values, for fuzzy sets u and v taking values in this new interval, the cross entropy is just given by this description here. Now, this is used as a notion of distance between fuzzy sets. And the idea is to use it somehow to better approximate the, find a better version of the graph in the lower dimensional space. So you start with the UMAP graph and run Laplacian Eigenmaps to get a low dimensional graph, which approximates it somehow with vertices p of xi, yi is p of xi, and edges with weights d of yi, yj given by distance now. And what you want to do is you want to adjust the vertices of this low dimensional graph by so-called minimizing cross entropy. And you do this by comparing weights. We have the weight of the graph, original graph, corresponding to this souped up epimetric d, but you adjusted that to find the weight you're interested in. But you have the weights that you started with for the distance between points, between vertices. But now you have the weight associated to the graph, the low dimensional graph given by distance between images. Okay, so you have two distinct weights, all right? And if you want to do this cross entropy thing, you want to and write it out, what you get is for these two choices of weights, you get some indexed overall pairs of elements in the original graph of this thing that I've just described, okay? Where, you use Wx and Wy instead of the weights that I started with originally. And so this Wx doesn't vary, that's fixed, that's the weights you started with, okay? So the dual doesn't vary either. So in order to minimize this number, you essentially minimizing that, the distinction between the weight and the distance in the target graph and the distance between the dual of the weight and the dual of the weight in the target graph. Okay, and I'm not going to say that I know better what stochastic gradient descent is, but you minimize this by moving the elements in the target graph in directions of negative slope, one dimension at a time. And when you've done that, whatever it is, you end up with a new graph, which is supposed to approximate your old graph that you approximated by, your old graph, which constructed by moving things around in the data set, or rather you find weights in the data set in a clever way. And you end up with a graph with weights defined by distance, which is optimally close to this UMAP graph, okay, which was what you wanted to do. And so you're not done. You have this weighted graph, right, where the weights are defined by distances. And so you essentially roll the topological data analysis tape on that by letting S vary, where S is the weight. And you have clusters for each parameter value S, and you have a corresponding hierarchy. And that hierarchy computes clusters in some sense. So what you end up with is a graph in a low dimensional space. The hope is that it detects clusters in the data set X, but this is not certain, okay? There is no cluster, none of these cluster techniques detect clusters with 100% certainty in high dimensional data sets. But so this is a good try, and it works better than a lot of other things in many, many examples, and there's been thousands of citations of the UMAP algorithm in the literature. But we still don't know how to reliably detect clusters yet. That's the big open problem in this game. Okay, I think I'm done. There are the references. Thank you very much.
Okay, thank you very much, Vic. Any questions? Okay, so one thing I want to ask Rick is the step where you describe the optimization, that's an extra step on top of the construction of the Y graph, right? So you had this dimensional reduction that you described earlier, and then on top of that, you apply this optimization that comes from this cross entropy.
Yeah. Yeah, that's what happens.
Okay.
Is that a question?
Okay, yeah, so one thing that's not really clear to me, how does the dimensional reduction helps us to understand the cluster better? I mean, so you're embedding a graph something by, I mean, you change the graph essentially, right, by embedding it into something else. From the weights, you turn the weights into distances, and in the reduction algorithm.
Yeah,
so
well, I mean,
how that helps. Maybe intuitively, let's say you have a data set that's quite simple on a two-dimensional Euclidean space, and you construct your gamma graph, and then you try to embed it into this other Euclidean space using this dimensional reduction. So you have this maybe extra freedom that you can play with.
Yeah, well, see, there's a lot of literature around this, and nobody's sure that they've got it. I mean, in all forms of data analysis, of these new constructions, they're shown to work in multiple examples. Okay. But in general, I mean, there's this, what we need is a sort of formal theory of dimension reduction, okay, which produces results that can be shown to work. And we don't have that yet. So what you're doing here is extracting features of the data sets with dimension reduction. Okay, and so you're clustering within those. And it's low dimensional features. Usually the D that you choose is 2 or 3. So you can actually visualize the thing in some plot. Okay. But what you're doing is comparing points, which are now projections of points in the original space. And of course, if you have a point in this projection and it's low dimensional, there might be a whole lot of points that map the same thing. So it's not really a graph embedding. You can fix that by changing the first eigenvector a little bit, but it's not clear at all that seeing a cluster in the projection is going to give you a cluster in the original space. Okay, it's a hope, and it is shown to work for certain examples, but there's no concrete theory.
Okay. And what is the motivation for the new cross entropy that is derived from
Well,
this
I
Shannon?
mean, if you look at the Healy-McInnes paper, it's essentially phrased in terms of fuzzy sets. Okay, and they wanted a way to compare fuzzy sets, and this is the only known way to compare fuzzy sets. But you end up with this horrific formula, and a mathematician would look at that and say, "What's going on?" And it's interesting that both the distance between points and the distance between their duals comes up. I mean, in this formula, that's an artifact of the formula, but maybe it's, I don't know. The right comparison tool, I don't think has been written down yet, but this works in many examples that Healy-McInnes work with, and if you talk to them, they don't use anything else. But this cross entropy is a distance thing. If you're thinking about fuzzy sets, that's a natural thing to think about as a distance between fuzzy sets.
Okay.
But it comes out of data analysis.
Okay. I see. Okay. So one other question that just it was something that you mentioned earlier in the slide about the excision. So that's is it the essentially the main place where we use the realization factor of this of Spivak's, because
Yeah.
we know that's there's a right adjoint, so that's the preservation. Yeah. Okay. We call it.
Yeah.
That's okay.
Yeah. Well, I mean, you have to prove this excision result, but that's the right. I mean, what that's saying is that the realization of Spivak stands in for the BilTop complex and your computing path components, and it's much easier to write down and construct.
Okay, I see. Okay, yeah, very interesting. Yeah. So maybe I can ask if there are any questions from the audience.
I had one that might be a naive one, so I apologize ahead of time. When you're doing the neighborhood, you're picking so many nearest neighbors. How are you using that value for how many neighbors you're looking at?
There's nothing about UMAP that's sort of independent learning, and that choice of number of nearest neighbors is one of the parameters that you have to feed into the construction as an operator. And I think it depends on how big a machine you've got.
Well, I was wanting to follow up on that in the sense of if you looked at some sort of intrinsic dimension for the data set, could you make a more intelligent choice based on, say, kissing number or what have you?
Maybe. As I said, there's lots of algorithms for this kind of thing. I don't know what more intelligent choice means, unless you assume that everything's near manifold. And maybe you could make a choice depending on being near manifold. But this manifold, I mean, what is it? So I'm inclined.
Right. Sorry.
Go ahead.
Right. I was assuming that you were taking the assumption that the data is lying roughly on some constant dimensional manifold.
Well, that's the standard assumption.
Right. So that you could then say that, hey, if I'm in 3 dimensions, then I don't want to just look at 2 nearest neighbors because that's not going to give me enough of a picture of what a reasonable neighborhood around me would look like.
Right. It would vary with the dimension of the manifold, certainly. I totally agree. But at the same time, this whole construction is simplicial sets. And the manifold construction, the manifold part comes in rarely. Only in the choice of weight for the Laplacian Eigenmaps construction. But if you look at that choice of weight, it essentially comes from the Shannon entropy function. So you don't have to do that choice at all. You could stay over in the real world of fuzzy sets taking values and numbers between 0 and infinity. That is the real world. That's where you start with that's where the calculations start, and I think that's where they should finish. So I have the short answer, I guess, is I haven't come to terms with choices of numbers of nearest neighbors, but it can vary. I mean, you know,
No, thank you.
these are,
One other thing, if you don't mind me asking, if I recall right, they're not doing absolute nearest neighbors just because of the size of their data sets.
that's right.
They're doing
So much,
nearest neighbors.
it's the one you can find.
How stable that is for them, and if you compare to the absolute nearest neighbors, because you're basically, if you're nearest neighbor, you're throwing them away from that neighborhood, aren't you?
Well, we're back in the realm here of producing, you know, diagrams of the torus Rips complexes as the choices of nearest neighbors vary. And there's a stability result for that I proved a few years ago. It's stability in the sense that one sees in ordinary clustering. Go ahead.
Cool. Thank you very much. I appreciate the answers.
Okay, thank you.
Okay, so any other questions? So if not, let's thank Rick. Thank you very much, Rick.
Thank you.